Welcome to part 3 of this video playlist about the best methods to alkylate alcohols. In this presentation, I'll show you how to use alkenes as electrophiles. When applicable, olefins are among the most inexpensive and environmentally friendly reagents for alkylating alcohols because no stoichiometric amounts of waste are formed. The alkylation of alcohols by alkenes can be catalyzed both by acids or bases. In the acid-catalyzed version, the olefin must first be converted into a carbocation by reaction with an electrophile. This can be a Brønsted acid or some electrophilic halogenating or thiolating reagent. The resulting intermediate carbocation will then react with the alcohol to form an ether and a proton. Because terminal alkenes will always yield secondary carbocations upon reaction with electrophiles, this strategy cannot be used to prepare unbranched ethers. When preparing tertiary acid-labile ethers or acetals under acidic conditions, one common mistake during workup is to add an aqueous base to the reaction mixture. This can cause a partial hydrolysis of the product because the initially added aqueous base will be completely neutralized and converted into aqueous acid, which can cleave tertiary ethers. The correct way to work up such reactions is to add the reaction mixture to an excess of aqueous base, not the other way around. The base-catalyzed version of this reaction only proceeds well with electron-deficient alkenes, or with alkenes that can at least form a slightly stabilized carbanion upon reaction with alkoxides, for instance a benzylic carbanion. Typical side reactions include the isomerization of the alkene or its oligomerization by reaction of the intermediate carbocations or carbanions with the starting alkene. The starting alcohol may also be dehydrated or converted into a symmetric ether, and the catalyst or other nucleophiles present in the reaction mixture may compete with the starting alcohol and lead to unexpected products. This is a typical acid-catalyzed addition of an alcohol, methanol in this case, to a simple alkene. A combination of iron chloride and toluene sulfonic acid was used as catalyst in chlorobenzene as solvent. In this instance, an excess of alcohol was used. This example is similar to the previous one, the main difference being that the alkene was used in excess. The yield of target ether wasn't high, probably because of Friedel-Crafts alkylation of the phenyl group by cyclohexene and the formation of styrene. Cyclohexyl ethers are, however, difficult to prepare from cyclohexyl halides or sulfonates, and acid-catalyzed alkylations with cyclohexene are therefore worth to consider. Phenols tend to be alkylated at carbon under acidic conditions. In this example, though, 4-nitrophenol was alkylated in high yield at oxygen by treatment with a large excess of allylarene in the presence of catalytic amounts of triflic acid. Potential side reactions were the Friedel-Crafts alkylation of the methoxyphenyl group and of the solvent toluene. Terz-butyl ethers are often used as protective group for aliphatic alcohols and phenols. These ethers are usually prepared under acidic conditions from isobutene or another source of terz-butyl cations, such as terz-butanol or MTBE. The example on this slide is a typical terz-butylation of F-mok-tyrosine methyl ester with isobutene and sulfuric acid as catalyst. No Friedel-Crafts alkylation of the hydroxyphenyl group occurred under these conditions. One peculiar but not very practical way to etherify alcohols with olefins is based on the use of stoichiometric amounts of oxidants and reducing agents simultaneously in combination with a cobalt catalyst. Although high yields can be attained under almost neutral conditions, mixing oxidants and reducing agents is potentially dangerous, and the high cost of the required reagents severely limits the usefulness of this curious reaction. Some alkenes, including electron-rich ones, can react with alkoxides and yield ethers, as in this example. Potential side reactions were nucleophilic cleavage of the methoxy group and aromatic nucleophilic substitution, but still a substantial amount of the target ether was obtained. With other non-activated alkenes than styrenes, the yield of ethers are, however, still lower. Electron-deficient alkenes, however, often react cleanly with alkoxides, as shown here. Particularly reactive are acrylates or acrylonitrile, while crotonates or cinnamates react more slowly, if at all. A high concentration of reactants can be of critical importance for the success of such alkylations. Because these are reversible, it is safer to work up these reactions by pouring the reaction mixture into an excess of aqueous acid instead of adding water or an acid to the reaction mixture. The addition of alcohols to electron-deficient olefins can also be catalyzed by acids, as in this example. Because the etherification was conducted without any solvent, the radical scavenger phenothiazine in combination with air had to be used to prevent polymerization. By the way, if you wonder how oxygen enhances the efficiency of stabilizers in preventing acrylate polymerization, the reason is the following. Carbon-centered radicals, as those formed during the polymerization of acrylates, are only moderately electrophilic and react only slowly with the electron-rich hydrogen atom donors usually used as stabilizers, such as diaryl amines or hydroquinones. In the presence of oxygen, however, peroxyl radicals are quickly formed, which are more electrophilic and react faster with the conventional stabilizers. The resulting hydroperoxides are quite stable at room temperature and do no longer propagate any radical chain reactions. For this reason, stabilized acrylates and other terminal electron-deficient olefins should be kept under air. This is, however, not the case for more electron-rich alkenes, such as vinyl ethers. As alternative to isobutene, terzbutanol or MTBE can also be used as synthetic equivalent of the terzbutyl cation. In this example, methyl mandylate was terzbutylated by treatment with MTBE and sulfuric acid. Instead of Brønsted acids, other electrophiles can also be used to convert alkenes into carbocations. In this example, an N-bromosulfonamide was used to bring about the alkoxybromination of cyclohexene, and the reaction was conducted in the alcohol as a solvent. Ethers and arenes can usually not be used as solvents for such reactions because these may react too. Here, for instance, THF was cleaved by the intermediate bromonium cation. Here are some further recent examples. A copy of this reference list can be found in the description of this video. The next presentation is about the formation of symmetric or unsymmetric ethers from alcohols as electrophiles and nucleophiles. See you then.